Hi, this is Dr. Khaleel Khan. Welcome to ACE Engineering College, the revision series, lecture series for revision of university exams of BTech students who are pursuing operating system course. So earlier occasion we have seen the chapter on CPU scheduling. So today, boys and girls, we are going to look into another important aspect of process management, namely deadlocks. As you know, deadlock is one of the important chapter in the process management in the course of operating system, where a lot of questions are asked in the exams, whether it is university exams, whether it is competitive exams. Essentially, you are going to expect a lot of problem from deadlock, a lot of questions from deadlock. And I would also say that from the placement perspective, you can expect some typical question being asked in the exam. So essentially from all these dimensions, right, all the spectrum, I would say, this is an important topic. And personally speaking, I would recommend that you want to read this chapter, you can follow the textbook of Galvin. Galvin is one of the good textbook for study of deadlock chapter, and in fact, all my slides, all my lectures, I'm going to take up on deadlocks, deadlock handling strategies from the textbook of Galvin. So first at the foremost, I would like to emphasize the definition of deadlock. What is the formal definition of deadlock we will see, okay? So let me write the definition here. Let me write the definition so that we can concentrate more on basic understanding. So let's say definition. We say like this: two or more processes are said to be in deadlock if and only the condition is they wait for the happening of an event. They wait for the happening of an event They wait for the happening of an event. They wait for the happening of an event which would never happen. Just rub off this. They wait for the happening of an event which would never happen. So, my dear students, I would like you to have a close look at this definition. Two or more processes. So essentially I'm trying to say that in order for deadlock to happen, minimum there should be two processes. Deadlock is not possible as such with regard to or with respect to resources with a single process. Minimum there should be two processes. So two or more processes are said to be in deadlock if and only if. What is the condition? The condition is that they should wait for the happening of an event which would never happen. Infinite blocking. So in other words, I would say that, in other words, they wait for the happening of an event which would never happen. Means infinitely they wait. So invariably, indirectly, I would say deadlock is nothing but infinite waiting. Infinite waiting for the happening of an event is deadlock. Generally, people ask, sir, what is the difference between starvation and deadlock? People often confuse between these two. So my dear students, please listen. Starvation is indefinite waiting, waiting for a long time is starvation, indefinite, waiting for indefinite time. Infinite waiting is deadlock. So that is the fundamental difference between starvation and deadlock. Essentially, both of them in fact are not desirable. We never want starvation to happen, but in addition to that, I would say deadlock is more catastrophic. Deadlock is more dangerous. Deadlock is supposed to be one of the undesirable feature of operating system. Let me write down. Deadlock is one of an undesirable feature. Deadlock is an undesirable feature of operating system. We never want deadlock to happen. Why? What is the reason for it? The reason is simple. The reason is simple. Why deadlock is undesirable? Let me write it down here. Let me write it down so that you can follow. You can easily understand. Because when deadlock happens, processes get blocked. Processes gets blocked while holding resources. Resources may be hardware or software resources, please. Resource can be a hardware resource or resource can be a software resource. So while holding the resource, process get blocked. So resource utilization will drastically come down. Since processes are blocked, they are not able to run on CPU. So eventually, consequently, what is the drawback of this? What is the consequence of this? This will lead to underutilization of resources. Underutilization of resources. Resource utilization will drastically come down. Plus, low CPU utilization. Low CPU utilization. So naturally, when CPU utilization is having an impact, so what is going to happen? What is going to happen because of underutilization of CPU? Throughput will come down. Throughput. I'm writing in short, hope you understand. Throughput, instead of writing the full word, I'm writing in short. Throughput comes down. So boys and girls, I am emphasizing that why we say deadlock is undesirable for the following reasons. These are the two essential reasons for deadlock being categorized as an undesirable event, undesirable feature of operating system. Underutilization of CPU leading to low throughput and low utilization of resources. So both of these features are not desirable. So in that aspect, we say deadlock is undesirable. So once we understand that deadlock is undesirable, so naturally and obviously, we would like to explore deadlock handling strategies. We desire that the operating system should support some deadlock handling strategies. So the main objective of this chapter is to study about various deadlock handling strategies. But before coming to that, we need to have some foundations as to what are the necessary conditions for deadlock to happen, and then what is the kind of system model are we assuming for the applicability of various deadlock handling strategies. So we have to build up the groundwork of that, okay? So but before coming to that, I would like to here give you some scenario, a simple scenario to illustrate the basic ideology of deadlock by means of some real life example. Let's imagine there are two people here. They have been named as Ross and Rachel, Rachel and Ross. So look at that. Rachel want to make an omelette for breakfast and Ross want to make a pancake. So they want a pan and they want some oil. So look at that. Rachel won't release the oil until, so right now we are assuming that the oil is in control of Rachel. Rachel gets the oil to start cooking and Ross grabs the pan. So both are essential for their food item. So this fellow Rachel wants omelette and Ross wants pancake. So essentially both oil and pancake are needed for these two items. So what is happening? Because the pan is under the control of Ross and Rachel holds the control of oil, so they make a request of each of them. So what are we saying? So point number one, Rachel gets the oil to start cooking, Ross grabs the pan. Both of them are holding the resources and waiting for other. Like Rachel won't release the oil until she gets the pan, and same thing happened. Ross won't release the pan until he gets the oil. So both of them are waiting for the event of releasing the respective held resources, which would never happen. Rachel become adamant and won't release the oil. Ross become adamant and say that, no, I won't release the pan until I get the oil. So these two events of releasing their respective resources eventually never happens, and that is nothing but deadlock. So my dear students, I just want to emphasize again and again that deadlock is like adamancy. Deadlock is like adamancy situation. Processes become adamant. So if you consider as an analogy, this is one process, that is other process, right? So they are holding this fellow is holding this resource, this fellow is holding this resource. And they are eventually waiting for each other resource that are held by each of them. And that event will never happen. So that is adamancy. So essentially the system will come to a grinding halt. And I would also like to tell you that in this scenario, deadlock is not just confined to operating system, as you see here. Deadlock can happen in families. I generally used to say ideological differences between family members could lead to deadlock. It may be brother and brother, brother and sister, wife and husband. If the ideological differences reach to the top pinnacle, then they become adamant. One fellow say, I don't agree with you. The other fellow say, I also don't agree with you. Let's stop talking. Right? So that is the crux, ultimate point of adamancy, situation leading to deadlock. So in any context, in any scenario, whether it is operating system or whether it is real life scenario, as you understand, deadlock is not a desirable situation. So boys and girls, to highlight the definition, I would say this is the best possible example. This is a formal definition of deadlock, I would say. There are two processes, process 1 and process 2. Process 1 is, and there are two resources, resource 1 and resource 2. Resource could be a hardware resource like register, memory, right? Register or memory. And software resource, maybe a semaphore or maybe some other software tool, file, it could be like that. So resource 1 and resource 2 are the two resources. Here, we are saying that resource 1 right now is under the control of process 1. And resource 2, for example, is under the control of process 2. It is saying assign. And further, process 1 say that I want resource 2. So process 1 holding resource 1, waiting for resource 2. So it is blocked. Similarly, process 2 holding resource 2 and waiting for resource 1. So essentially they are forming a cycle among themselves. Look at that. This is a cycle. And that is deadlock. So this is a clear definition of deadlock. So my dear students, essentially in your exam, if they ask you formal definition, define deadlock, or they say explain deadlock for 2 or 3 marks, this is what you need to explain. I gave the formal definition. If you observe, you need to write this, right? They may ask you what is the consequence of deadlock, why deadlock is undesirable. I have written down here, right? This is a formal definition, this is a consequence of deadlock. And better you can draw this diagram, or if you want, you can give this example to highlight the philosophy of deadlock. So this is going to cover the question of what is deadlock, why deadlock is undesirable, what are the consequences of deadlock in the system. So these questions are covered by this topic which I have given so far. Okay, so that is the scenario. Now, as I said, to build up understanding with regard to deadlock handling strategies, I said you need to have some basics. So first basic coming up is called system model, meaning what kind of system are we assuming for the study or implementation applicability of various deadlock handling strategies. So here, boys and girls, look at this. We assume our system consists of finite number of resources, R1 to Rm. As I mentioned, resource can be a hardware resource or a software resource, like CPU cycles, memory space, IO devices. Each resource type Ri has WI instance. Instance is nothing but number of copies. Instance is nothing but number of copies. How many copies of that resource are available in the system? Like, for example, register is a resource. Register is a resource, category of a resource. I may have one register, single instance, or I may have more than one instance, multiple instance. Okay? So multi-instance resource, instance. Each process utilizes a resource as follows. This is a very important life cycle model, please. Every process has to basically request. Every process has to basically request the resource. Depending on the availability of the resource may be granted or may be denied. If it is granted, the process will use the resource, and eventually when the usage is over, the process will subsequently release the resource. So this is the paradigm. You won't say that the process first will use and then will make the request. That's not correct. We'll have to request first, then the operating system as a resource manager would grant the request or deny the request. If the process request is denied, the process will have to wait. If the resource is granted, the process will use the resource and eventually, finally, will release the resource. So releasing is voluntarily. There is no involuntary or forcible release. Are you getting my point? We cannot take away the resource forcibly from the process. Process would voluntarily release the resource. So that is the system model, very important to keep in mind. So what is characterization? Characterization means basically like, I generally tell the students that for any problem to arise, there should be some necessary conditions. Without necessary conditions, problem doesn't arise. So my dear students, I generally used to give this example that malaria, for example, is a disease. So in any area, if the disease malaria, which is our problem, is going to arise or is to happen, then what are the necessary conditions? What are the necessary conditions for the disease like malaria to happen in area, to erupt in any area? You would definitely say mosquitoes. So my dear students, mosquitoes become a necessary condition for a deadlock. Then for mosquitoes to breed, what is the requirement? Stagnant water, untidiness, uncleanliness, right? Unclean environment. So these all become the necessary conditions for the problem of malaria to happen. Is it not? So exactly in the same way, in order for deadlock to happen, there are necessary conditions. So this is a 5-mark question which you can expect in your exam. What are the necessary conditions for deadlock to happen? Or this could also be asked in the interviews, okay? So there are 4 necessary conditions, boys and girls. Number 1, mutual exclusion. Mutual exclusion implies the presence of what are called shared resources or critical section. If there are shared resources or critical section, then you have to ensure the principle of mutual exclusion. And in doing so, quite number of times deadlock may happen. So therefore, in any IPC environment, when there are shared resources, mutual exclusion principle become mandatory or compulsory. So therefore, that eventually will become one of the necessary conditions for a deadlock to happen. Then what is the second necessary condition? Second necessary condition, as you saw, is hold and wait. Meaning, the process should hold some resource and wait for another resource. So please remember, if there is no hold and wait, there is no deadlock. But every hold and wait does not imply deadlock because it's necessary condition. Just like we say, wherever there are mosquitoes, we don't say malaria will erupt. May or may not. That is the meaning of necessary condition. So if these conditions are prevalent, deadlock may happen, may not happen. But these are necessary for the problem to arise. If any system malaria is there, means mosquitoes must be there. So that means if deadlock is there, there must be hold and wait. If deadlock is there, there must be mutual shared resources. That is what I am trying to say. So every hold and wait, like if you see the previous example here, there is hold and wait. How? Look at that. Process 1 is holding resource R1 waiting for R2. Process P2 is holding resource R2 waiting for R1. There is hold and wait, there is a deadlock. There is hold and wait and there is deadlock. So hold and wait become a necessary condition for a deadlock to happen. So a process holding at least one resource and is waiting to acquire additional resources held by other processes. So in addition to that, there are 2 more other conditions necessary: no preemption and circular wait. No preemption, I told already. No preemption implies, boys and girls, please understand. No preemption implies, so let me mark it here with a different thing so that you always remember. No preemption means nobody can forcibly take away the resource from the process. Process will release as per system model the resource voluntarily on its own. No preemption. All right? So no preemption. Resource can be released only voluntarily by the process holding it. After that, the process has completed its task. Otherwise, if you enforce preemption, if you allow preemption, deadlock may not happen. Deadlock may not happen. So that is no preemption of the resource become the necessary condition for a deadlock. Next, last condition is circular wait. Processes must form a cycle among themselves in order for a deadlock to happen. So if there is no cycle, there is no deadlock. If there is cycle, there may or may not be deadlock. If there is hold and wait, there may or may not be deadlock. If there is a deadlock, there must be hold and wait. So finally, eventually, I'm saying that in any operating system environment, in the presence of these 4 necessary conditions, what are they? Mutual exclusion, hold and wait, no preemption, and circular wait. Circular wait, see that there is a clear cycle among the processes. I've already shown there is a cycle. P1 is waiting on P2, P2 is waiting on P1, cyclic condition. So if you want, you can draw it with more number of processes. You can draw with more number of processes, like P1 is waiting on P2, P2 is waiting on P3, P3 is waiting on P4, P4 is waiting on P1. 4 processes forming a cycle among themselves. So don't think that circularity should happen only among 2 processes. It can happen between more than 2 processes. So 4 conditions are necessary for a problem of deadlock to arise. Chaliye, aage badhenge. We will look into the other aspects. We have a tool called resource allocation graph, which is going to characterize the system in terms of deadlock. And also it is going to play a very important role in the study and implementation of various deadlock handling strategies. Like generally, we define a graph in terms of set of vertices and set of edges. We generally define graph in terms of set of vertices and set of edges, right? So like that, resource allocation graph is also defined in terms of set of vertices and set of edges. Resource allocation graph is also defined in terms of set of vertices and set of edges. Set of vertices and set of edges. So let me just reduce the size again. Okay. Right. So let's see here. This is okay. What are the kind of vertices? So here, there are two types of vertices. One is process vertex and the other is resource vertex. Process vertex is indicated by a circle and resource vertex is indicated by a square or rectangle. And resource, as I said earlier, can have single instance or multi-instance. So how are we going to do that? So P is a set of processes, R is a set of resources, and the edges are of two types, request edge and assignment edge. Request will go from process to resource and assign is from resource to process. So I will show you in the next page. Look at that. So this is how I indicate the process. So boys and girls, this is a process indicated by a circle. If you want, you can write the name of the process outside. These are resources are shown by a rectangle. And these dots indicate the number of instances. Process PI requests, I have to put a line like this. Process PI requests some resource, one line. Process PI is assigned one copy of it. So this requested is assigned it. Right, this is an example of resource allocation graph. If you make a study, if you make a careful study of this, resource allocation graph, you can check. There are three processes, P1, P2, P3. There are four resources, R1, R3, R2, R4, multi-instance, multi-instance, single instance, single instance. P1 is holding this resource R2, waiting for this. P2 is allocated these two copies, waiting for this. And so right now, none of the copies, look at this. Right now, none of the copies of R4 are in use. All are free. Suppose at this point of time, P1 and P2 are blocked. If P3 makes a request for R4, can it be granted? Yes, it can be granted. I will put a assigned it like this. And after that, if P3 further requests a copy of R2, none of the copies of R2 are free. So if P3 makes a request for a copy of R2, it will get blocked. All three processes are blocked. So let me say undo here, and then draw a clean line. Okay. So this is blocked. Is this a deadlock? Yes, there is a deadlock. Because we have a cycle, we have hold and wait, right? There is no possibility whatsoever for the processes to come out from the block state. Look at the clear cycle. So cycle in resource allocation graph with multi-instance resource become a necessary condition for deadlock. It become a necessary condition for deadlock. Deadlock is there right now. In no situation that the processes P1, P2, P3 can come out from their block state. No situation. No situation exists for them to come out from their block state. That's why there is a cycle, there is a deadlock. But however, if you consider, so this is the same thing I'm doing. You look at this second graph, second example. Boys and girls, please have a close look at this. I have four processes, P1, P2, P3, P4, two resources, R1 and R2. Both are multi-instance. Do we have a cycle at this juncture? Yes, sir, we have a cycle. The cycle is there. Look at this cycle. Let me draw it. There is a cycle. But does this cycle imply deadlock? No, there is no deadlock. Why? Because if this process releases the resource, it can be granted to this process. There is a possibility of breaking the cycle. So what I wanted you to remember and conceptualize is that if there is any potential possibility of breaking the cycle in the resource allocation graph, there is no deadlock. There is no deadlock. In earlier example, there was no possibility of breaking the cycle, but here we have a possibility, so therefore there is no deadlock. So what is the characterization that we are going to make here? We are going to say that every cycle is not deadlock, but every deadlock implies cycle. If there is a cycle, there may be a deadlock, may not be a deadlock. By means of these two clear examples, I have demonstrated that. So now the nutshell, the basic facts with regard to cycle in resource allocation graph are as follows. If graph contains no cycle, absolutely no deadlock. This you have to conceptualize. Right? So what I'm trying to say, look at that. There is no deadlock if the graph contains no cycles. If graph contains a cycle, and if there is only one instance, so naturally there will be a deadlock if there is only one instance. That is very obvious. I don't have to emphasize. I don't have to tell you. But if several instances are there, possibility exists. There may be a deadlock, may not be a deadlock, as we have seen in the previous examples. Okay. Now finally, based on this, I would like to tell you what are the methodology for dealing with deadlock. What are in general the methods available for dealing with the problem of deadlock. So I would basically say explain to you by taking a suitable example, by writing down the hierarchy here like this, So see here, boys and girls. Strategies, or I would say deadlock handling strategies. Deadlock handling strategies. how are we going to deal with deadlock handling strategies? What are the general approaches for dealing with the problem of deadlock? So let's analyze here, let's see it here. So please concentrate. Essentially, there are two approaches. One is called proactive approach, where we try to prevent the deadlock, prevention. Second is avoidance. So in my own terminology, I would say that these two are like proactive in nature, proactive. Proactive means essentially these will not allow the system to go into deadlock. Beforehand we are taking some action. We are never allowing the system to go into deadlock state. We prevent it, we avoid it. But how? We have to see that. We will see later point of time. And then the other taxonomy, as part of the taxonomy, the other concept is here I would write detection and recovery. That means we allow the system to go into deadlock. We detect it and then we recover it. Detection and recovery. And there is one more approach. The last approach is called ignorance. Okay? It's called ignorance. And in the literature, I would like to tell you, in the literature, some algorithms, some names are given to these strategies. Like ignorance is called ostrich algorithm. And avoidance is called in the literature as banker's algorithm. So before continuing with these strategies, I would like to start or make a definition with regard to ignorance first. Why is it called ostrich algorithm? As you popularly know, that ostrich is a bird that is generally found in the deserts. So ostrich, whenever it finds some danger in the desert, generally the sand dune, so what it does is, out of anxiety, out of curiosity, it digs a hole inside the sand and then put its small head along with part of neck inside the sand. The very popular image you can see in Google Images, ostrich algorithm. So it digs a hole inside the sand and take a careless, lethargic attitude of trying to see that now I am totally safe. The whole body is outside, only the small head and the neck is inside the hole, and it closes its eyes, feels that I am perfectly safe. That is called ignorant strategy of ostrich. So when the sandstorm comes, it will be washed off. Sometime luckily get saved, and other time it get crashed. So that is the ignorant strategy of ostrich. So invariably, I'm just trying to tell you that, right? Invariably, I'm just trying to tell you that ignorance basically means no strategy, boys and girls. Ignorance means no strategy. You don't have any strategy. You're not applying any strategy. You're not dealing with deadlock. So then in that case, what are we going to do? Like I say, most of our contemporary operating system like Unix, Linux, and Windows, they adopt ignorant strategy. That means what? That means when deadlock occurs, like ostrich, we are supposed to take some risky action of restarting the system. Right, when the system gets halted, system gets stuck, I restart. That restart is nothing but the action being taken by ostrich, like ostrich. So the system may come up or the system may get crashed. So that is called ostrich algorithm. So here, Unix, Linux, and Windows, they adopt deadlock ignorance strategy of not dealing with a concrete approach for dealing with deadlock. Why? There are reasons. I don't want to venture into this limited time lecture. Why is it that Unix or Linux or Windows do not deploy or employ deadlock handling strategy? That I would leave it as an exercise for you to explore and find out why our contemporary desktop operating systems, they do not deploy or use any deadlock handling strategy. You can do that. Okay. Now in some cases or such cases where deadlock handling is mandatory, where you can't afford your system to go down for a while, you can't afford the system to lose out any information, then deadlock handling strategies are mandatory. So in that case, my dear students, you can deploy either prevention, you can go for avoidance, you can go for detection followed by recovery. So we'll briefly try to cover up all these strategies one by one. So methods for handling deadlock. So here is the summarized discussion which I made just now. Ensure that the system will never enter into deadlock. This is done by means of prevention or avoidance. Allow the system to enter into deadlock state and then recover, detection and recovery. Ignore the problem altogether and pretend that deadlocks never occur in the system. As I said, used by operating system like Unix. So whatever I told is penned down here in the slides for your ready reference notes. So first approach is, boys and girls, first approach of dealing with deadlock is prevention. How is deadlock prevented? Just I would say in one line here, deadlock for your short notes, I would say like this. So please understand and keep in mind. Deadlock is essentially prevented by dissatisfying one or more of the necessary conditions. This is the working line of deadlock prevention, or you may say, for example, this is the algorithm for deadlock prevention. How is deadlock prevented? 1 mark question in interviews. For example, I'm saying deadlock is essentially prevented by negating, dissatisfying, right, not holding the necessary conditions. See, idea is very simple. We have seen that in order for deadlock to happen, 4 conditions are necessarily to be present or prevalent in the system. 4 conditions are necessary to be present in the system. Mutual exclusion, hold and wait, no preemption, and circular wait. So 4 conditions are present, deadlock can occur, deadlock can happen. So if you don't want those conditions to happen, if you ensure that my system would never have hold and wait, if you ensure that my system would never have circularity, if you ensure that my system would never have no preemption, if you allow preemption, how and why deadlock will happen? Deadlock never happens. So boys and girls, understand conceptually as a lifetime concept, right? Not forgetting for lifetime is that very simple. Deadlock is essentially prevented by negating one or more of the necessary conditions. So what we have to do, one by one we have to take a condition and see, can we negate it? Can we negate that condition? If so, how? At what cost? If so, how to negate it? What are the protocols, approaches for negating that condition? And what will be the consequence of negating that condition? That is what we need to learn. So my dear students, we will take up one by one, right? We will take up each of those necessary conditions one by one, and we would see how we can negate it. How we can negate it, at what cost and what protocol. So let's start, mutual exclusion. We said that mutual exclusion is mandatory in the system. Mutual exclusion is necessary in the system for deadlock to happen, right? So mutual exclusion implies the presence of shared resources, critical resources. So it means very simply that if you want to negate mutual exclusion, if you want no mutual exclusion principle to be applicable or present in the system, your system should never have any critical or shared resources. So can we imagine a system without a shared resource? Impossible. Impossible. I would say it is impossible. A particular multi-programmed operating system cannot be thought of having at least one shared resource. So therefore, we say in summary, it's not possible to deny, negate mutual exclusion. So out of 4, 1 is gone. We cannot prevent deadlock by negating mutual exclusion. Then what are the other conditions? The other conditions are, first among them is hold and wait. We said that if the process is holding a resource and waiting for another resource, possibility of deadlock. So negating hold and wait means the process should not be holding and waiting, means or wait. So in short, I say hold and wait is negated by implementing the rule of hold or wait, hold or wait. Either should be holding or waiting. So that's what. Must guarantee that whenever a process requires a resource, it does not hold any other resource. That is what we are trying to say. Does not hold any other resource. So require processes to request and be allocated. This is first protocol of ensuring hold and wait. Let the process request and be allocated all the resources so that it will be only under holding condition, no waiting. So this is one approach. But this will have a consequence, lower resource utilization, starvation possible. Because the process may have to wait a long time to get all resources, starvation. If it get all the resources and not using it, is it not? Process runs in phases. So during phase 1, if I don't, I'm holding it and keeping it idle, underutilization of resource. So that's not desirable. Inefficiency could arise. So that's the reason why we don't prefer this condition. Then do we have other approaches? Yes, we have other approaches. Process should release all the resources before requesting a new resource. So that can be done to avoid underutilization of resource. But there are other conditions we will see, like for example, no preemption. So to deny no preemption, you can go for preemption. You can enforce preemption. I can follow forcible preemption, or I can follow self-preemption. Both are possible for this, but the common drawback of this again would be starvation. So let's make a study. If a process that is holding some resource, requests another resource that cannot be immediately allocated, then all resources currently being held are released. Self-preemption. So my dear students, this is called self-preemption. Go for self-preemption. Preempted resources are added to the list of resources for which the process is running. The process will be restarted only when it can regain its old resources as well as the new ones that it is requesting. So that is the point. So if the process is released of all its resources, it will have to restart again and again, request the same old resources and new one, and continue its execution. So that may lead to starvation, because if this idea of preemption is happening very frequently, then eventually starvation would happen. How to implement a negation of circularity? How to avoid circularity? How to prevent circularity? By implementing a total ordering of all resource types, and require that each process required resources in an increasing order of enumeration. So rather than that, like for what I generally used to give this example, follow me carefully, please. Follow me. Suppose, for example, if I have some process PRI, it is holding the following resources, let us say. It is holding the following resources A, B, C, D. And using these resources, it has come up to this point of execution. So let's say the number of resources is 3, this is 5, this is 8, this is 10. So it's following linearity. So that means following the total order relation, this process is all eligible to request any resource whose number is greater than 10 to maintain the linearity. Otherwise, for example, instead of requesting a resource which is greater than number 10, this is a resource number 10, if it requests, for example, resource number 6. So where do 6 lie? Between 5 and 8, 6. So that means from 10, you are coming back to 6. This is circularity, So we should avoid that circularity. So simply terms, circular weight condition is prohibited, is prevented by enforcing a total ordering, means total linear order on all the processes making requests for resources. So if this can be done, then the problem of circularity can be avoided at the cost of the problem of starvation. Again, at the cost of the problem of starvation. So starvation may happen because if the process, what will happen? Suppose the process say that, I'm sorry, along with D, I compulsory need this resource number 6. Then I will have to release these resources, high numbered resources than 6. And then request 6, and then again request 8, then again request 10. So in the course of time, when I request 8 again and 10 again, there is no guarantee that I will get it back immediately. The process may have to wait for some time. So that is starvation. So my dear students, in a nutshell, what I wanted to emphasize and tell you, that it is definitely possible to prevent deadlock by dissatisfying, by negating one or more of the 3 necessary conditions, namely hold and wait, circular weight, and no preemption. Because mutual exclusion is non-compromisable, But what is the consequence of it? The consequence is, in general, starvation. Starvation may happen to processes because of negating one or more of those necessary conditions. So this is a summarized discussion with regard to deadlock prevention. Now come to deadlock avoidance. As I said, this deadlock avoidance algorithm is popularly known as Banker's algorithm. Why is it called Banker's algorithm? Because the situation which is used here in this algorithm is similar to a banking situation. Just like the bank, the customers go and present their checks for withdrawal of amount, the strategy which is adopted by the banker is similar. So in that sense, this algorithm is named as, the way it works is just like a banker works. The banker will not give your amount directly or immediately. It may say deny the request depending on the available cash, depending on the availability balance. Based on that, the request may be granted or may not be granted. So the paradigm of working of bank exactly emulates to this approach, and that's why this approach is called Banker's algorithm. This algorithm was proposed by our famous computer science, professor of computer science by name Edwin Dijkstra, recipient of the first Turing Award. So he proposed this algorithm, Dijkstra's algorithm, Banker's algorithm, deadlock avoidance. So I would like to re-emphasize to you, retell you the same thing, that if the system deploys deadlock avoidance, then also deadlock does not happen. Deadlock does not occur if I use deadlock avoidance. This is based on, I will write in short, this is based on a concept called system state. This is based on a concept called system state. At any point of time, the system is said to be either safe or unsafe. Safe is like deadlock, sorry, the safe is like no deadlock. Unsafe is like a danger, potential possibility of a deadlock to happen. And the basic core objective of Banker's algorithm is to always operate the system in safe mode. Never allow the system to go into unsafeness. Never allow the system to go into unsafeness. And what are the parameters, the data structures that are going to govern the system state? That we need to make a study. Then I will take one simple example and show you how it works to ascertain, to find out whether the given state of the system is safe or unsafe, and how the request made by the process, can it be granted or not? That is the resource request algorithm. So therefore, boys and girls, I just wanted to tell you that the Banker's algorithm essentially has two sub-algorithms. Banker's algorithm, you need to learn from the perspective of your examination. From the perspective of the examination, I would say Banker's algorithm, there are 2 points. One is safety algorithm. So both of them you can expect as long type questions in your exam, and the other is resource request algorithm. Other is resource request algorithm. The resource request algorithm. So let's make a study. Requires that the system has some additional a priori information. A priori. A priori means beforehand. What is that beforehand information? Every process is required to indicate to the operating system what is its maximum requirement of every resource. Every resource. That is called a priori information. So example available. So most useful model require that each process declare its maximum number of resources. Then deadlock algorithm dynamically examine the resource allocation state to ensure that there is never a circular wait condition. Resource allocation state is defined by the number of available and allocated resources and the maximum demand, as will be followed in the subsequent size. So when a process requests an available resource, the system must decide and immediately allocation leaves the system in a safe state. That means after seeing that the resulting state is safe, then only we grant the request. If the resulting system is not safe, we don't grant. That is the basic ideology. So the basic ideology of working of Banker's algorithm is request initiated by the process will be granted if and only if the resulting state is safe. If the resulting state is unsafe, request is not granted. Request is not granted. Request is denied. This is the basic ideology of it. Okay. So safety algorithm would test whether the resulting state is safe or not. Okay. So what are the parameters? So see here I have written the definition. System is in safe state if there exists a sequence like this of all processes in the system such that for each process the resources can still request and be granted with the current available resources. If the current need of the processes are satisfiable with the available resources in some order, then we say the system is safe. Otherwise, if it cannot be satisfied in any order for all the given processes, then we claim the system is unsafe. Again and again I am telling, unsafe is not deadlock, right? Every unsafe is not deadlock, but every deadlock means unsafe. So we venture into deadlock from unsafeness. Unsafe is like a warning. You have to be careful. If you are not careful in unsafe state, you would eventually go into deadlock state. Okay? So that is if process PI request resource needs are not immediately available, then PI can wait until all PI other processes have finished. Okay? So when PI is finished, PI can obtain needed resources, execute, return, allocate resource, terminate. When PI terminates, PI plus one, next process can continue in that way we can say. So here these are the consequential points. The summarized. If a system is in safe state, no deadlock. If a system is in unsafe state, possibility of deadlock. So this is warning, that's what I said. This is like warning. And avoidance is ensure that system will never enter into unsafe state. The basic objective of Banker's algorithm is to always operate the system in safe state. That is what you have to always remember in your mind. System is safe if the needs or requirements of all the processes can be satisfied in some order. That's it. That's the core logic. So in the interview, people may ask you, what is the basic ideology of Banker's algorithm, avoidance algorithm? How is deadlock avoided? Deadlock is avoided simply by always operating the system in safe mode. System is said to be safe if and only if the need of all the processes can be satisfied with the available resources in some order. Request initiated by any process will be granted if and only if the resulting state after granting the request is safe. That's it. If you tell in this way, you are completely knowledgeable with regard to Banker's algorithm. So boys and girls, this is a simple Venn diagram to show the scenario of the safe, unsafe and deadlock state. So this is safe state, no deadlock. Unsafe and deadlock is a subspace of unsafe state. Subspace of unsafe state. So avoidance algorithm, there are two. Single instance, that is a trivial one, we don't go into it. Multi-instance, these are more important one. When resources are multi-instance, how do we deal with deadlock avoidance? So for multi-instance, each process must a priori claim maximum use. When a process requires a resource, it may have to wait. When a process gets all, it must return them infinite. These are the ones. So boys and girls, I would just like to quickly tell you what are the available data structures here. So first we have n number of processes, number of resources, these are available copies of resources. These are a priori information max. Every process will have to announce to the operating system what is its maximum requirement. That maximum requirement is monitored in this data structure max, which is a n by m matrix. Allocation is also an m by m matrix indicating what all resources are currently allocated to the process. Need is the current requirement. What is my further need? So need is nothing but max minus allocation. Max minus allocation would give you need. So this is a safety algorithm where we are going to check whether the need of all processes can be satisfied in some order with the available resources. This is algorithm describing that scenario. Okay, so this is a safety algorithm. And this is a resource request algorithm to decide whether request initiated by any process should be granted or not. Like first step we say request, here we say request should be first less than or equal to need. That means this is within the balance. If this is not within the need, then we say it is an illegal request. Then the request is within the available or not, we have to check. Do I have sufficient balance? Then we assume to have satisfied the request. So when we assume to have satisfied the request, these are the changes that we need to make. Current available gets subtracted by request. Allocation will get improved by request. Need of the process will get reduced by request. And then we run the safety algorithm to check whether system is safe or not. If resulting state of system is safe, grant it. If it is unsafe, deny it, because we are going into unsafeness. So this is a simple logic to ensure that. This is a simple example. This is the current, it got relocated. Let me write available is this. This is available. Available of ABC. Or let me write so here I will write available. It got relocated ABC 332. So boys and girls, these are the matrix you can see. This is allocation, this is max. So based on this, you will have to first compute the values of need of the processes for the resources ABC. What is the formula for need? We said max minus allocation. So if I first calculate the need of process P0 here, so max minus allocation, max is 753. Look at this. This is max. It got relocated. This allocation. It got relocated. I'm sorry for that, right? So because of formatting of the software, it got relocated. So these are like ABC, right? So for this ABC you're about. These are processes. The allocation is maximum. So need is nothing but max minus allocation. So what will be the need of the process P0? 743. 753 minus 010, 743. What will be the need of P1? 322 minus 200. So it become 122. What will be the need of P2? P2 will be 902 minus 302, 600. 600. What will be the need of P3? 222 minus 211. It will become 011. What is the need of P4? 433 minus 002, 431. So with these available, can I satisfy the need of these processes? Yes, we can satisfy. You can check. At time T0, I am trying to check. Please see here on board. Please see here on board. In what order can we satisfy the need of the process? Can I satisfy the need of this? No. Can I satisfy the need of this? Yes, sir, we can satisfy. So if I complete P1, what will my new available become? 332 plus current allocation of P1. Current allocation of P1 is 200. So it becomes 532. Now with 532, next I can satisfy the need of P3. Next I can satisfy the need of P3, 011. It can be met from 532. 600 cannot be satisfied because this fellow wants 6, I have 5. Then after that, after P3, the current allocation of P3, which is 211, is added to it. So it will become 743. 743. With 743, next I can take up P4, for example. Completing P4 will improve the available to 745. How? 743 plus 002, 745. After that, I can take up P0. P0. So it becomes 755. And with that, next I will take up, lastly, P2, 1057. It will become 1057. Look at that, 1057. I got back total number of copies, 1057. So I claim that system is safe. This is how I decide whether system is safe or unsafe. This safety algorithm. And like that, when a process makes a request for some resource, we can check whether that request based on resource request algorithm, can it be granted or not. So after checking the safety algorithm, if the system is arising to be safe, we grant the request. If it is not, we deny the request and block the process, as simple as that. So you can expect a full 10-mark problem on Banker's algorithm in your exam. So make yourself well familiarized, do some practice as I have done here, right, to test whether system is safe or not, to check whether request initiated by any process, can it be granted or not, same thing here. Then finally, my dear students, we have the last strategy coming up, and that is nothing but deadlock detection and recovery. As I said, if you deploy deadlock detection, it means that you allow the system to go into deadlock. Allow the system to go into deadlock. Let deadlock happens. Let deadlock happens. Then we have approaches for detecting the deadlock and recovering. Generally, in my terminology, I used to say that this approach is just like a doctor, just like a patient visits a doctor when he sees some symptoms, when he sees some problem. He approaches the doctor. Doctor listens to the story of the patient, and then he expects something. Okay, this fellow may be having this problem, typhoid, malaria, something. Then he will subject the patient to the test. So based on the symptom given by the patient, the doctor is making some analysis, making some assumption that maybe this fellow is having this problem, that problem, or that problem. To ratify his assumption, to ratify his guess, he subject the patient to a test. The result of the test may be positive or negative. If it is positive, he will start recovery. If it is negative, he will tell the patient, enjoy life, nothing to worry about. Same way this approach works. When the system has some symptoms, then the deadlock manager will activate the deadlock detection test. The result will be positive or negative. If it is positive, we start recovery. If it is negative, then we continue the system without any operation. So first we have detection approach and then recovery. There are two modules here. One is detection, look at that. One is detection, the other is recovery. For detection, again, there are two types of algorithm. One is single instance resource, the other is multi-instance resource. Two detection algorithm. One for the case when system has got single instance resource, all resources are of single instance type, and the other is for multi-instance type. Single instance type is done by wait for graph. I will show you here diagrammatically. This is my resource allocation graph where primarily I assume, look at this, boys and girls. Here I assume all resources are having single copy, only one instance like this, only one instance like this. So we have 5 processes, P1, P2, P3, P4, P5. 5 resources, R1, R2, R3, R4, R5. P1 is holding resource R2 waiting for R1, and like that it goes. So from this resource allocation graph, we clearly see that there are block processes, P1, P2, P3, P4. 4 processes are blocked, and that is a symptom, boys and girls. That is a symptom. That is one of the symptoms for the deadlock. So what will the operating system deadlock manager does? From this wait for graph, from this resource allocation graph, it will derive this meta graph. It will derive this meta graph by name wait for graph. This wait for graph, as you are seeing here, boys and girls, as you are seeing here, does not have any resource vertex. It has only processes as vertices like P1, P2, P3, P4, P5. How our resources are basically merged, are collapsed. P1 is waiting on P2 for resource R1, so we remove this and put a direct link from P1 to P2. This is called wait for H. Likewise, P2 is waiting on P5, P2 is waiting on P3, P2 is waiting on P4, all wait for edges. So after this wait for graph is derived, what are we going to do? We are going to run cycle detection algorithm. detection algorithm. Algorithm to detect the presence of a cycle. To know whether there is a cycle in the resource allocation graph or not. Do we have a cycle? Yes, sir, we have a cycle. Sir, what is the largest cycle? The largest cycle is P1, P2, P3, P1, P2, P3, P4. This cycle implies deadlock because the instances are single instance. In the single instance resource, whenever there is a cycle, there is a deadlock. So we have a deadlock. So this is the output of this algorithm, boys and girls, this is output. So these deadlock processes will become like victim and they will be subjected to recovery. So the output of this algorithm are deadlock processes, and these deadlock processes will go as input to recovery module, will go as input to recovery. So all these are victims. These are the victims. So these victims are taken by recovery module to take appropriate action for recovery. But before looking at the recovery approaches, I would like to emphasize this is the general algorithm. I would say this is general algorithm, boys and girls. This is a general algorithm for detection. General, I mean I can have multi-instance resource, and the way it works is just like safety algorithm. So I don't have to tell you much about this. The way it works is just like safety algorithm. So the data structures are available, allocation, request. Instead of need and maximum, I have request because it is realistic. There is no condition that the process will have to maintain a priori information. There is no demand like that. We have reality. Process will have allocation, process will have request and available. If the requests of all the processes are satisfiable with the available resources, system is safe, no deadlock. If the requests of all processes cannot be granted, cannot be satisfied with the available resources, system is in deadlock. So let me write that point for your convenience here. If the request of all processes can be satisfied with the available resources, in some order, then system is safe. By system saying safe, by system saying that it is safe, it means clearly, it means no deadlock. It means deadlock. Otherwise, means you cannot satisfy, there is a deadlock. This is a simple algorithm, bacho. Boys and girls, this is a simple algorithm. Otherwise, there is a deadlock. And all those processes, like earlier occasion, whose requests cannot be granted, they are said to be in deadlock. And those become the victim that will go as input to recovery strategy. That's it. That's all is the concept, no rocket science. Very simple approach. So this is the data set will be like this. I'm leaving this as an exercise for you to work out. Right? I have number of processes. This is the current allocation. These are request matrix, the available matrix. So you can put a line to draw it. So with this available, I can satisfy the request of P0. After P0, I can take up P2. After P2, I can take up P3, then P1, then P4. I can satisfy the request. So no deadlock. The system is safe. Even though there are 3 block processes, but still system is safe. But later, if suppose P2 makes a request as 001, then eventually deadlock will happen. And all the process excepting for P0, everybody will be in deadlock. So P1 to P4, deadlock processes will go as output of this algorithm, will go as input to recovery module, recovery strategy. So lastly, we would see what are the general approaches of recovery. For recovery, I would pen down here for your convenience. I would say that for recovering the system from deadlock, recovery modules or recovery strategies, I would say kill the process. Abort the process, I would say, abort the process. And the other approach is resource preemption. Resource preemption. These are the 2 general approaches for dealing with recovery. Abort the process means kill the process. So within that, again, I can have 2 approaches, kill all or kill one at a time. Kill one at a time. Kill all means all the deadlock process which we told earlier, P1 to P4, they are all killed. You have to restart again from beginning. That is very disastrous because some processes which were nearing to completion also get killed and you will have to restart again from beginning. On the other hand, if you want to save some of the important processes, then you can be slightly graceful in killing, don't be harsh in killing. So kill one at a time, take one victim, kill it. But there is no guarantee that you will come out from deadlock, so you'll have to apply recovery again, detection again. So in kill one at a time strategy, you will have to kill one process by applying some criteria, and then you have to apply detection again to know whether deadlock is overcome or not. Deadlock is overcome, be happy that you have saved some processes. But if not, select another victim, kill it again, and continue this until deadlock cycle is broken. That is the idea. So the main idea is here, don't have to apply deadlock detection again. Here you have to apply deadlock detection multiple times. So that's pros and cons. That's a relative comparison between both the approaches. The third approach of dealing with recovery is altogether different, resource preemption. In resource preemption, we never believe in killing the process. We never believe in killing the process. Okay? We assume that the problem of deadlock essentially happens due to lack of resources. So rather than killing the process, we will preempt the resource from the process, latest resource. From all the 3-4 processes who are in deadlock, we take away some resources, and then we'll roll back the process to the state of from where they got the resource. That is called resource preemption with rollback. So let me add that term. Let me add that term, rollback. This rollback is an overhead here. That's a cumbersome job. That's a cumbersome job, rollback. So checkpoints you have to maintain in processes, that's an overhead. And again, you will have to apply detection like earlier occasion. But the advantage is you don't have to restart the process from beginning. That is the advantage of resource preemption with rollback. So whatever it is, whatever be the approach, kill all, kill one at a time, resource preemption, eventually we say there would be a problem of starvation because there is no guarantee that a process may be getting preempted of resources very frequently, or process may get killed multiple times and eventually get starved to complete. But this is one approach of dealing with. So this is the recover, that is what I have penned down here, about one process at a time until the deadlock cycle is eliminated. So questions to be addressed here in this issue is, we have to see the priority, how long process has computed, resources that the process has used, resources process needs to complete, how many processes will need to be terminated, is process interactive or blocked. These are the various questions that I have to observe for selecting a victim to minimize the cost, right? So recover, resource preemption, these are and the last point I said, starvation problem. So that is all about recovery strategy, okay? So these are the consequences of various deadlock handling strategies. So as I said in my summarized discussion, contemporary desktop operating system like Unix, Linux, and Windows do not use any deadlock handling strategy. Deadlock handling strategies are mandatory in operating system where we can't afford our system to go down for a while, even for 1 second, and we can't afford to lose out even 1 bit of data. So in such cases, deadlock handling strategies are applied. So this is what I have from my pocket today for the chapter of deadlocks. I hope this makes much sense to you. Important question being, what is the concept of deadlock, consequence of deadlock, characterization of deadlock, like resource allocation graph, necessary conditions, and then deadlock handling strategies like, for example, deadlock prevention, deadlock avoidance through Banker's algorithm, deadlock detection and recovery. These are the 3 major topics which you can expect in your exams as major questions. So my dear students, prepare on these lines. And this 1 hour, we are trying to make these videos in short and sweet and up to the mark, covering up comprehensively, acting as a good revision for you before your exam. So if you watch this video before your exam, I'm very sure this will act as a necessary thing and you can very easily write the exam with this revision. Okay? So that's it from my side. Thank you very much. Have a good night.